So hello everyone, welcome to our RM seminar. So it's our great pleasure to welcome Greg Buhr, who is the engineering manager of control design product of MathWorks. So Greg got his bachelor, master, and PhD from the School of Mechanical Engineering at Purdue, and he has joined MathWorks since 2003. So he has been the leading force behind many of the toolboxes that we all use in MATLAB. And recently, they also worked on a very interesting toolbox that has to do with reinforcement learning and control. So Greg and I, we met many years ago at the controls conferences, and since then we have been really good friends. So please pay attention to his talk. He has very interesting things to tell you, and he will be happy to answer any questions. So Greg, the room is yours now.
All right, thank you for the introduction, Kyriakis. Thank you for providing me for the seminar series. I appreciate the opportunity to speak to your guys' groups. So today's topic is reinforcement learning and how you can leverage deep learning for control. So the agenda, we'll be focusing on a particular example of how to train a biped robot to walk. And through this talk, I'll go in through what is reinforcement learning, how would you solve this problem using a traditional controls approach, and then how will we apply reinforcement learning to solve this problem, and then wrap it up with some Q&A. So what is reinforcement learning? So reinforcement learning is a subset of machine learning. A lot of times when you say machine learning, most people are familiar with unsupervised learning and supervised learning. Unsupervised learning is when you have unlabeled data and you're trying to gather some information about your data, such as using clustering. Supervised learning is when you have labeled data and you do either classification or regression. This is, most common of doing image classification is this picture of a dog or a cat. And then finally, the third type of machine learning is reinforcement learning. And this is when you use interaction data. So you don't have actual labeled data, but you need to interact with your environment in order to make control and decision-making processes. One thing that differentiates reinforcement learning from other machine learning techniques is that the sequence of actions or decisions that you take matter. For example, if you are doing image classification, it doesn't really matter if you say this is a dog or a cat or what order that you do it in, but when you're interacting and making decision-making process, they're temporal and time and sequential. So if you can imagine if you're driving a car, it matters whether or not you turn left or right at the previous time step. So reinforcement learning is about learning a behavior or accomplishing a task through trial and error, through interaction. And sometimes you'll see the term deep reinforcement learning, and this is when you use a deep model to solve complex problems. So there's a lot of applications for reinforcement learning. Some of the most popular that you see in the news is with video games. You see stuff with the Atari games, AlphaGo beating the world champions. So there's a lot of video games and game type applications that we see in the news, which is very exciting. But it can also be used for autonomous vehicles, controls of such as drones, and robotics. And the robotics applications one we'll focus on today. So our goal today is to train a robot to walk in a straight line. So how would we go about doing this? So we have several motors that actuate the joints of the robot, and we need to determine what is the sequence of motor commands that we need to use to make the robot walk, right? So by selecting the right set of motor commands, we can get a locomotive behavior from the robot. And so typically you do this with control, right? So we have a system here. We provide some actions to the system, which results in a resulting behavior. And the goal is how do we determine what actions generate the behavior that we desire? And typically, if you're familiar with feedback control, this is a standard problem where you observe the behavior. This could be observing the behavior through different sensors, such as encoders, accelerometers, vision systems, etc. You take these state observations and you compare them to what your desired behavior is, and then the controller works on this error from the desired behavior and the actual behavior of the system to determine what actions it should take next to try to achieve the desired behavior. And this is the concept of feedback control. So applying this to our robot system with the traditional controls approach, Here we have observations, so we could have camera data coming in and sensors coming in from encoders from the joints, accelerometers, etc. And we want to determine data information from the system. To start out with, typically you would do some perception. You might have a vision perception engineer extract features from this camera data. And then using the sensor data with these visual camera feature extraction, you would do some sort of sensor fusion and state estimation or localization to get information about your current pose, where you're at in the environment, your current state. And then you would feed these states into a control system to determine what motor commands you should use to generate the desired behavior. And in this case, we have 6 motor commands. We have one for the hip joint, knee joint, and ankle joint for each of the legs. However, it's a little bit more complicated than this even. If we drill into the control system, we'll see that there's actually a large number of other items that we would do in developing a control system. We'd have low-level motor controllers such as PIDs to make sure that the motors are going to the desired reference trajectories and speed and location. We'd have leg and trunk trajectories, so these might be pre-planned trajectories that we're then using as reference commands to track. And then we might also have some outer loops, which are balancing the robot for external disturbances or uncertainty in the system to account for. Excuse me. So you can see this can be a very complicated problem. It can actually span multiple disciplines from perception, sensor fusion, as well as control. So could we look at an alternative approach to solve this problem? So what if we said, what happens if we took all this stuff and lumped it into a single black box controller? So here we want to take the camera data and the sensors, put it into a controller and generate the motor commands explicitly. So this would be nice if we were able to do this, but the question is, how do we design this complicated black box system? And one way is reinforcement learning. So what is reinforcement learning? So we'll use the definition that Sutton Bartow used from their famous reinforcement learning book. Reinforcement learning is learning what to do, how to map situations to actions to maximize a numerical reward signal. The learner is not told what actions to take, but must discover what actions to take by learning what actions yield the most reward by trying them. An easy way to think about this is teaching a dog new tricks, right? So I have a dog here. The owner yells fetch and throws the stick. So the observation the dog sees is the stick flying and the owner yelling fetch. The dog may decide to fetch the stick. It may sit down. If it fetches the stick and comes back, you give it a reward, a treat, right? So you're reinforcing a behavior that you want the dog to learn. And so that's the principle that we're doing. If you ever trained a dog, you'll notice that it's a lot of interaction getting the dog to do the right item. And then once it does the right action, give it a reward, and then it reinforces that behavior over and over again. So before we get into solving the reinforcement learning problem, I'll go over some of the terminology that's used in reinforcement learning. So there's 2 main components. There's the agent and the environment. So the environment would include the robot or any physical items that's being interacted with. And the agent is really about the logic that used to take observations and sense action. So you can think of it sort of like the brain. In this case, the observations would be like joint angles, acceleration, velocity, the camera vision system, etc. And the actions that will be sent to the robot are the motor torques to each of the joints. In addition, the environment provides a reward, stating how well did it do? How's it doing for these given actions that it's taking? So if we look at this in terms of the reinforcement agent, we want to learn the optimal policy. So this is the same diagram, just drawn up a little bit different. So we have a policy here. It takes the observations and maps it through a function to determine the actions. And we have a reinforcement learning algorithm. And the reinforcement algorithm takes what current action the policy took, what are the current observations and the current rewards being received. And the reinforcement learning is used as optimization to find an optimal policy that maximizes the long-term reward. So The goal of the reinforcement learning algorithm is how it should update the policy to maximize its long-term reward. So what is the workflow that we would use to solve this problem? So there's several pieces. So first, we need an environment. What are we interacting with? We need to define a reward signal. The reward signal is very important. It determines what task we're trying to solve. We need a policy. So this is the function that we're using to make the decision process. We need an agent to train. So the agent will be training the policy to maximize its reward. And then finally, you might want to deploy. This could be depending on whether you're training in simulation or hardware, but eventually you want to deploy to a hardware device. So let's first focus on the environment. So the environment, like I said, is everything outside of an agent. It provides the observations, the state of the environment, which is observed by the agent. The agent provides the action, which then modifies if we move the joints of the robot, it changes the state of the environment, and the environment is also returning a reward based upon the current behavior of the system. In our case, we have this biped robot that we'll be using. We'll be mainly using it through simulation, but we'll talk about what are some of the advantages of learning on hardware versus simulation. And as I mentioned, we'll have a large number of observations. It's localization information as well as its joint information, etc. And the actions that are going to the robot will be the torques going to each of the motors for each of the joints. So there's two ways you can interact with the environment. We can look at real versus simulated environment. So on the left here, we have a real environment, which is the actual robot. And then here we have a simulation environment, which could be like Simulink, where you develop a simulation environment that represents the real system. So one of the benefits of using a real environment is accuracy, right? So there's no model mismatch. You're learning on the actual system that you're trying to train. So accuracy is a big plus here. One of the downsides is risk, right? So as you learn and do interaction, you have to try and explore various activities, right? So I have to explore in order to see whether or not I can achieve a better behavior. If I explore poorly, let's say I'm driving a car and I turn left into a wall, so you really have to worry about safety and other things as you learn. In addition, learning with reinforcement learning is very sample and efficient. You need a large number of samples to learn with reinforcement learning, and therefore it could cause wear and tear on your actual robot. One of the benefits of using a simulated environment is training speed. So in the real environment, you can only train at real clock time. A lot of times you can run simulations faster than wall clock time. So you actually include training speed as well as using multiple resources such as cloud computing and distributing these simulations across multiple computers. It also provides flexible simulation conditions. There may be some conditions that you wouldn't necessarily be able to get the robot in real life, but you can create these types of simulations with different initial conditions or different scenarios within a simulated environment. And as I mentioned before, a key part is safety. You don't have to worry about during exploration whether or not you take a bad action that could potentially damage a robot in real life. So safety is a big critical here, or injure somebody else. The downside is model inaccuracy. So, your simulated environment may not model your real environment exactly. This could be due to exogenous disturbance or just the physical dynamics of the system. However, there are a lot of tools that you can use to improve models, such as parameter estimation and so forth, to improve the how well the simulated environment maps your real system. So with that being said, we'll be focusing on a simulated environment. Here we're using Simulink to model the biped robot. We're actually modeling the robot using our physical modeling toolboxes called SimScape. And we're able to model the dynamics of the system as well as the contact forces with the environment. So if we take a look into this model here, we have a couple blocks. We have the agent block, and then the walking robot, which represents the environment. We represent the robot's legs, left and right. We have some sensors. We have our world and ground, hips and torsos, etc. And then we use the physical modeling package to represent each of the revolute joints and legs of the system. If we look into the sensors, we're measuring quite a few parameters of the system, which we'll be feeding back into our observations. The next piece I want to talk about is the reward. So now that we defined the environment, we want to focus on what is the reward for the task that we're trying to solve. So as I mentioned, the reward is a function that outputs a scalar number that represents the immediate goodness of an agent at a particular state taking a particular action. And our goal is to maximize this long-term reward for the system. So in defining the reward, how do you translate in a behavior into a numerical value, right? So we have to create a numerical value which encodes the behavior that we're trying to learn. So you can think of it as, how do I incentivize the robot? So is this the way you want me to go? Put some money out in front of the robot. So what we did was, this is the final reward function that we came with, and I'll go into further detail about how we came about it. But our reward is our current forward velocity, which is our goal. We want the robot to walk forward. We also don't want the robot to stray too far away from the straight line, so we have a deviation from the center line as a penalty. We also want to make sure the robot stays upright, so we want to keep the robot at some nominal height. So we have a nominal trunk height that we want to maintain. So as it deviates, it penalizes from that. We want to make sure it walks as long as possible, so we're giving it a reward for each time step it remains upright. And we also want to minimize actuator effort. So we actually penalize how much torque are we providing to each of the motor joints. So defining the reward system in Simulink is quite easy. We have a block here where a subsystem which we model. If we look inside of it, we actually just build up this reward using the block diagram. You could also use a MATLAB function block to actually just explicitly write this equation as well. So it's very easy to define a reward system in this modeling infrastructure. So now that we've defined the reward system, the next step is to define the policy that we're using. So as I mentioned, the agent, the policy is inside the agent. And so if we look inside of here, just to recall that, the observations, the policy is the function that maps the observations to the actions. And then we'll also use the reinforcement learning algorithm to optimize this policy. So inside of this particular example, we'll be using the actor-critic method. And to kind of give a description of how actor-critic methods work, there's two neural networks, and typically they're tuned simultaneously. So we have an actor, which takes the state observations to provide actions, right? And the actor is trying to learn what is the best action to take given the observations. And then the critic is used to try to estimate the value of each state action pair that the system takes. And this value represents how good that action was, what's the expected long-term reward for taking that action for the robot in that given state. And using this critic, we can actually criticize the actor in terms of, we can use the critic to improve the actor's behavior. As I mentioned, the critic represents the value, and the value is the total reward the agent expects from a given state and taking actions onward. So how does this work? So the actor is responsible, as I said, taking the state observations and creating an action. The critic then takes the state observations and the action that the actor took and predicts the value of that action, the long-term reward that would be received. And basically it takes that value and compares it with the reward signal that comes back. And basically using the Bellman equation, we can look at how far does this deviate? How well is the critic representing this expected value that we expect based upon the new reward coming in versus what its current parameterization is. And using this error signal, we can update the critic so that it does a better job approximating what the value is for a given state and action pair. Then once we have a good critic, basically the critic then uses this information to update the actor based upon its knowledge of what actions are good for particular states. So creating the agent, we're going to use a reinforcement learning algorithm called deep deterministic policy gradient. And in constructing this, we need to create a critic network, a policy network, and then also we have to set some associated hyperparameters with the system, and I'll go through how this is done in the reinforcement learning toolbox. So first we need to create a critic network. So this takes in state observation and actions and returns a value. Here we're using the deep network designer and the deep learning toolbox to build the network. Here we have the observations coming in. There's a few fully connected layers with some ReLU layers, and then the action coming in through fully connected and on a final ReLU and fully connected layer. So that represents the critic structure that we'll be using for this example. Similarly, we can use the deep network designer to create a actor network. Here we have the observations coming in, and we have a few fully connected layers with ReLU activation functions. And our final layer in our actor network is a TANH layer, because we actually want to keep our torque outputs between plus and minus 1. So we're able to put our actuation constraints explicitly in the actor policy. So to create a DDP agent in the toolbox, we can specify the options for each of the actor and critic. So these are hyperparameters such as what type of optimizer that you want to use. Do you want to use something with momentum or a stochastic gradient approach? Do you want to do regularization as well as the learning rate? So these are some of the hyperparameters that you specify. We create the network with the networks that we defined in the previous step. And then there's also some other hyperparameters that we can specify, such as the discount factor, mini batch size, and et cetera, that these all go into how the agent does its updates for the reinforcement learning algorithm. In addition, you can specify your noise options. So this is about how the agent will go about exploring its environment. Once we have the networks created, we can then construct our agent with the actor and critic representation and the associated hyperparameters that we want to use for the reinforcement learning agent. So now that we define the agent object, we can basically use the Simulink block. We have a reinforcement learning agent block in Simulink, so you can drag that in and put that agent in the mask of the system. So now that we define the agent in the system, the reward function, in the environment of the walking robot, the next step is to train the agent. So training our agent, there's several choices to do it. We can accelerate by running simulations in parallel. This can be done on multi-core computers or clusters or in the cloud. So basically we have a client, we have several workers. So the client tells the workers to run some simulations. When the worker's done, it sends the data back, and then the agent updates itself, and then this sends out to the workers to do additional simulations. So this greatly accelerates the learning process by distributing the simulation workload. We also support training with GPU, so you can run the inference or the critic on GPUs. This is typically more beneficial the deeper your networks are. CPUs typically run faster for shallower networks because of the overhead of transferring data to the GPU memory. So training the agent's pretty simple. We specify some training options. What's the maximum number of episodes that we want to run for training? What's the max number of steps that we want to take per episode? what is the stopping criteria for training? So here our stopping criteria is when our average reward reaches a particular level. During training, we are using parallelization, and we're sending experience back after every 32 steps the agent takes, or the worker takes. And this is done through these parameters of the options. And then basically we just call train on the agent environment and the training options and let it run. So here's a video of it running. Initially it's running at real time here, and then eventually we speed up the thing for time purposes. But you can see the number of episodes. You can see it starting to run. Initially, we don't see it learning very much at the beginning, but once it learns to take a few steps, the learning actually improves quite a bit. So once it learns to take a few steps of walking, it actually improves its learning quite a bit. Here we have a dip. So one thing's interesting with a lot of reinforcement learning is you'll go through these peaks and valleys of learning on many of the methods. But the good news is the trend is moving up. So our walking is improving the more samples that we take. And so here we see we ran 2,418 episodes. And then finally, with that trained agent, we press play to walk with that trained agent. You can see that the agent's walking well and walking along the straight line. As it starts to deviate, it moves back to the center line. So here we saw, an accelerated view of the training process and the final results of it walking. But let's look a little bit more detail of how we got here. Oftentimes you need to do reward shaping as part of the training loop. Oftentimes you'll see that the agent's having trouble learning, so you want to give it more incentive to learn and improve sample efficiency. So oftentimes there's a little feedback loop that you go through adjusting the reward system or the reward function. So why does reward function matter so much? So if you just started out, you might say, I want my robot to walk forward. So let's start out by just creating a reward, which is just purely forward velocity. So as we ran this with just this reward, it tended to get stuck in a local minimum of wanting to just fall forward. So it gets initial forward velocity. If we trained it longer with more exploration, maybe it would eventually learn to walk. But there's not much guiding the robot of what type of behavior it should be trying to achieve. So the next step we did was, let's add a reward for each time step the robot remains upright, and also give it a penalty for not maintaining a certain torso height. So if we do this, we see that the robot does a better job of walking. However, it's not ideal. It's very zombie, very non-smooth. Looks like it's going to fall over a few times, but manages its balance. But it did do what we wanted to do. We wanted it to move forward and maintain a torso height. So the next step, what we did was, let's add an additional penalty for the energy used for actuation. So here we added a penalty for the energy used in the motor torques for each of the joints. So we look here, we see we start getting really good walking behavior, right? And it's walking more like a human. And if you think of a human evolved to have pretty efficient walking behavior, so it's kind of expected that this type of behavior would emerge as you start to penalize actuation and you want more efficient movement. However, you saw that the robot doesn't really maintain the center line. You can see that it deviates from it. And we never really told the robot explicitly in this reward function that was part of the task. All right. So the next step, what we do is we added a penalty for deviating from the center line. So if we look at this, once we do that, we see that we get good behavior of walking. We see when it starts to deviate from the center line, it starts tracking back to the center line. So the main key takeaway from here is reward function matters. The sample efficiency of a reinforcement learning object or reinforcement learning algorithm learning a particular behavior can be dramatically affected by how you incentivize the agent through the reward function. So now that we have a trained agent that we like, we did this through simulation. Now we want to deploy it onto a real robot. Currently, there's a couple ways you can deploy to target. So here we have our offline simulation. We have a reinforcement learning algorithm, the policy, and then the simulated environment. And we're going to take this policy and put it onto the target hardware to see how well this policy works in the real environment. And you can do this in the reinforcement learning toolbox to automatically generate C or C++ code for the policy, as well as CUDA code if you're running on a GPU to run the policy on an embedded device. So basically the way it works, it takes the policy, it goes through our CodeGen products to automatically generate code. Using MATLAB Coder, GPU Coder, we can deploy to different libraries such as Intel MKLDNN, NVIDIA TensorRT CUDA libraries, or ARM compute libraries. So the key takeaways from my talk is that we can use reinforcement learning to solve complicated control and decision problems. One of the nice things about reinforcement learning is we saw a large number of observations coming into the control system. Typically, you would have to use perception and sensor fusion to reduce those into a manageable subset that a controller could use. But reinforcement learning scales up well for observing a large amount of information and determine the appropriate action. Reward shaping is very important in improving learning outcomes. We find this is one of the more trickier parts in terms of coming up with good reward functions that improve sample efficiency as well as map out the desired behavior that you want your agent to learn. And then MATLAB and Simulink with the reinforcement learning toolbox provides a complete workflow for deep reinforcement learning. So here we went through the example for this biped robot. This is a shipping example, so you can actually find it in our documentation as well. So that ends my presentation. I think I went through it relatively fast, but I'm happy to answer any questions.
So thank you very much, Greg. So it seems that we have one question. Is this example available in MATLAB already?
Yes, it ships with the toolbox. We also have
toolbox does it use? That's the second one. So if you can say also the toolbox.
Sorry, I didn't see the second one. So the reinforcement learning toolbox requires the deep learning toolbox. So that's what's required to run reinforcement learning itself. In this example, we also use Simulink and SimScape multibody to model the robot's dynamics. So for the environment, it would also require Simulink as well as SimScape multibody. We ship this example with the product. We also have some videos. If you go to our MATLAB Tech Talks, we have a series of videos on reinforcement learning, and this is part of one of the examples that we've leveraged there.
Craig, any more questions for Craig? So Craig, you have used this for the walking robot. Have you tried anything? I think you tried also some real applications with some companies. I know you cannot talk about those, but what is the scale of these applications that you have successfully tried, this toolbox and these results that you presented?
Yeah. So we've worked with a lot of customers. We probably engaged with probably over 150 customers on various applications. We see a lot of problems in terms of scheduling. So a particular example might be where you're trying to schedule maybe pumps. If you use a simple problem, let's say you have 5 pumps pumping water to a water tower, and you're trying to meet demand for the water supply. How do you optimize the scheduling of those pumps to minimize costs while satisfying the demand and variations in the demand? So we see a lot of those. I mean, that's an abstract representation, but we see a lot of scheduling type problems We've seen problems in radar and communications. We see a lot of problems in heavy equipment. So there's a large number of applications that we see a lot of customers are leveraging. We have a lot of customers that previously currently do a lot of stuff with dynamic programming, and they're looking at, can they reduce the overhead of an engineer solving the dynamic programming problem using reinforcement learning. So that's another area as well.
So there is a lot of questions in the Q&A. So let me, okay, so Noah asks, how long did it take real time to train the biped robot?
I need to go back to the simulation. Where was it? The real time. Unfortunately, we have this in seconds. So 19,514 seconds, and I'm not good at doing math in my head. So that's how long the actual elapsed time from the training. And I think we had 8 workers. So I can't do that math in my head, sorry. 19,514 seconds.
So Zhao asks, in the example, it appears the real robot application does not have a reinforcement learning module, but rather a policy module. Is the policy not updated in the real robot application?
Yeah, so we didn't actually deploy this to a real robot yet. But if we did, we've deployed in the reinforcement learning algorithm, or the policy to some simple examples where we have like a BeagleBow Blue, where we've done some experiments where we deployed the policy to hardware. We currently don't support learning on the hardware itself explicitly, only deploying the policy, and we're currently working on providing functionality to actually learn directly on the hardware as well.
So Anonymous asks, is it possible to import network weights? Will it be compatible with other common packages such as PyTorch?
Yeah, so we have, so there's a thing called ONNX. I forget what ONNX stands for. It's like Open Network Exchange. So ONNX is a generic format, which many of the popular frameworks support as a intermediate representation or a compatible representation. So if you look, we support ONNX import. There are some layers that we don't support. So what happens is if you import a network that may have a custom layer in PyTorch, or maybe a layer that we don't have explicitly, it'll put a placeholder layer for it. But if you go to our documentation page, it documents all the layers that we support. We support all the popular ones. And it's one of our popular features of ONNX is the popular way of converting networks from different platforms.
And is it compatible with PyTorch, the Python?
Yeah. So it's compatible with PyTorch. I don't know if it's TensorFlow explicitly, but Keras, there's an importer for Keras as well. But yeah, it's all the most popular packages leverage this ONNX Open Network Exchange framework. And that includes network weights as well as the structure.
So Mohamed asks, in simulation, how does the training process work? Do you first collect data and then train the policy on it? Or is the policy trained online? I think you partially answered this question. Yeah,
the policy is actually trained online. So it's different than supervised learning, although you can take if you have what you call an off-policy method for reinforcement learning, you can use previously collected data and learn from that data. But this is continuously running simulations and then learning while you're running the simulation. So it's dynamically updating the policy as you learn. Typically, this is much more, you usually get much better results in this type of way than trying to do a purely supervised learning aspect, because it'll actually tend to converge better to an optimal solution.
So another person asks, is there access to these presentation slides? Quite informative. So if you can
I'll
share.
about providing access to the slides. I can follow up with Kyriakis on
Okay.
that. I do know that that you guys are planning to publish the recording.
Okay, so another person asks, what does the critic network do again?
Yeah. So the critic network is trying to figure out, given an action or given the current state and the action you take, and then if you're following, let's say, the optimal policy, what is your long-term reward? So it's trying to figure out how good the action that you took was. And if you think of the word critic, right, it's if you're going to criticize something, right, like an actor critic, like if you're going to criticize somebody's performance, you associate a value to that, right? So that you can think of the critic as evaluating the actor, saying, I give you a 1, I give you a 10, and then then the actor uses that information, or the learning algorithm uses that information to make the actor achieve better scores, or better evaluation from the critic.
It's like a movie, people were, España, when I used to be in Santa Barbara, she was like, oh, this actor critic is like a movie, right? So you have the actors and then you have the critics.
Yeah.
So Jennings said, do we set the reward from the start, or do we set a naive or a trivial reward first, then modify the reward or add more components to the reward if the training results are bad?
So typically, in any type of, especially deep learning type of stuff, the more knowledge you can, so some people, when they look at reinforcement learning, they're trying to minimize, not put much information into the reward function. This can be done with like the Atari games where, the score is the reward function. You may not know how it's computed or care. But typically in engineering applications, you want to try to embed your domain knowledge into it. By embedding some domain knowledge into the reward function, even if we just set the reward function as forward velocity, we may have been able to get it to learn if we actually, did enough exploration. But it may take a long time for it to get there. So if you can put some domain knowledge into the design of the reward function, you often improve the sample efficiency of which you learn. But you can start with a naive type of thing. Typically, what we do is that we think we have a good reward function. We kind of evaluate what kind of behavior emerges from it, and then look at, are there things that we could use to further encode the behavior. Sometimes it's hard to define a task in terms of a numerical value, right? There's oftentimes playing with the weights. Do I care more about tracking? Do I care more about actuation effort? Similar to like if you did a L-cube type problem, how do you adjust the Q and R weights of the function, or of the cost function?
Another question is how easy it is to import a run or robot model in this framework. It seems that biped example is written from scratch.
Yeah. So with Simscape, we actually can import CAD models. So we have several examples where we've imported a different robot arm from the CAD models explicitly. You have to sometimes do a little bit of cleanup of the model, but the CAD model has all the joints, the joints and rigid bodies in it. So that's typically, if we have a CAD drawing of the system, we'll use that to import into the system. You can also, if you have your equations in MATLAB, or if you want to leverage things such as a robotic system toolbox that has some simulation models in it already that are parameterized, you can leverage those as well. But it's pretty easy using Simscape. You basically, set the inertias and stuff of each of the rigid bodies and what type of joints they are. It's pretty straightforward to create. And we have examples, documentation examples and videos of how to design this explicitly.
So Nicholas asks, is the best way to build the reward function to just train and add to it until it completes the task? You also...
Yeah, I think adding your domain knowledge into the reward function is key. uh, it's kind of like, did you provide enough information to solve the task? Sometimes, some things are obvious that you made a mistake when you see the behavior emerge. When one reward function that we did was just forward velocity and minimize actuation. And what it did was it tried to do the least amount of motion that it could to make it fall forward. Least amount of torques to make it fall forward, which makes sense, right? You're trying to make it move forward, but you're also trying to minimize how much control effort you use, right? And so the behavior, emerged where it just used just enough actuator effort to make it fall forward. So sometimes when you see that, you can say, well, I want it to remain upright, so let me try to maintain its torso to a certain level.
And let's see, do you have a convergence analysis to prove that under your self-designed reward, it will finally converge to the suboptimal solution?
Yeah. So one of the challenges with reinforcement learning, Kyriakis probably knows more about these proofs than I do, but whenever you have a nonlinear function approximation, none of these methods really guarantee convergence that I'm aware of. If you have linear policy and critics, there's some proofs that you can guarantee convergence on. But typically you can't guarantee convergence, and you'll see a lot of different algorithms, such as like DDPG, TD3, time delay. I forget what all the acronyms stand for. SACS, stall factor critic. Some of these methods trade off convergence versus sample efficiency. They don't necessarily guarantee convergence in all cases, but they actually tend to have better convergence properties. Do you have anything to add to that, Kyriakis?
Yes, yeah. So I think, so we really need, to develop this convergence. We need to, but I think you use DDPG, right?
Yeah.
So this already converges. So there are proofs for it. So I guess since you guys are using DDPG for such framework, you probably get the convergence by it.
Sometimes it depends on sometimes it depends on what type of policy and they're using. For some of the nonlinear policies, there's different convergence conditions.
Yeah. So another person asks that you have already answered. Any suggestions for reward functional design? You already answered this one. Zhao Yang asked, how is critic trained online? Is the role of the critic to determine a reward of the action? If so, how do we ensure the output quality from the critic convergence to an acceptable level? You also partially.
Yeah. So as I mentioned before, if I go back to this slide here, so the critic actually takes the reward coming in. So we have what the current estimate of the value of the critic is here, right? And then taking this reward and the next state in actuation value, we can determine what is the new best estimate based upon our current data. And using this, then we can use it's a Bellman equation to provide an update to the parameterization of the critic. So the critic is continuously learning as well, and basically the critic is good when basically this error goes to zero for all states and actions.
How would you tune those parameters in the reward function?
So much like other type of methodologies, a lot of times whenever you have a cost function or a reward function, coming up with relative balances between these, sometimes it's a matter of normalization. If you get all these signals on the same scale, then it's easier to weight them on equal grounds. Where if each of these values are very disparate in magnitudes, then you need to account for that in the weight. So one way is to kind of normalize all your components of your reward function and then start tweaking the weights based upon the level of importance that you want. Are you more worried about it stringing from the path, or are you more worried about it staying upright? So there's kind of a trade-off to that. So much like any optimization function that you write, there's doing scaling and then balancing the weights based upon your desired objectives.
What are the two variables a comma b in the reward equals function a comma b? Cannot recall. Thanks.
The state and action. Sometimes there's also the next state as well. Meaning if your next state took you into a bad location, you have the next state. But yeah, so typically reward is a function of the state and action, and also sometimes of the next state resulting from that action taken in that state.
What happens if the state space or action space is continuous when you try to maximize the Q? Do you take gradients?
Yeah, so actually it uses a gradient-based method to compute to update the network weights. So in this case, the actions were continuous.
And I think one last question by Buhr. Could you shed some light on off-policy versus on-policy methods?
Yeah. So off-policy and on-policy. So the main difference, so if you hear stuff like policy gradient, et cetera, those are on-policy methods. And on-policy methods means that you need to learn from the data that the policy is running. So if I have a particular set of parameters for the policy, when I do my update, I have to use the data from that policy. So if I collected data previously, changed my policy, collected some more data, I can't use that first batch of data anymore to update my policy, because the method means I have to use data that was generated with that policy. I know I'm being wordy here, but and then off policy means I can actually learn from data from another policy, meaning I could have a whole nother policy running, or I could have data collected, with the same policy, or I guess it's a different policy. It has a different parameterization. And one of those things is nice is that you can use stuff such as replay buffers, where you store previous states and actions and reuse that data over and over again. Off-policy methods also allows you to, let's say you ran a whole bunch of experiments in the past or training a different agent, you could still run that data through an off-policy method and reuse that data that you previously collected. For example, if you had some data that you collected from another controller on a hardware experiment, et cetera, you could still leverage that data on off policy. So it just means that I can use data I can learn from data that was generated with a different policy. Those are off policy methods. On policy means I can only use data generated with that policy.
So yeah, in off policy learning, we use what is called the behavioral policy. So this is not the actual policy, but it's a behavioral policy. And then that's why it's called off policy. But yeah, and I think pretty good. I think we asked too many questions, Craig, and there is one more. Okay, let's answer one more, and that's it. So since you know the desired behavior, you can turn your reward if the kind results are not good enough. Yet, what about the cases that even yourself, you don't know the desired behavior?
Yeah, I mean, so you have to have some way of encoding the behavior, right? If there's no feedback of telling you whether or not you're doing something good, there's no way you can react to how I should change my behavior. So, I mean, even if you think of a dog or a kid, you give verbal feedback, or you clap or do something exciting as feedback without some sort of reward. There's no way to incentivize behavior. So you may not know the reward function explicitly. There are things called inverse reinforcement learning. This is where let's say you have an expert driver or operator, and you want to learn what is the reward that makes that person an expert, right? And so there's sometimes it's called inverse optimal control or inverse reinforcement learning, where you have a policy which you say is optimal, and I want to know what is the cost or reward function that makes that person is trying to achieve. So that's one way. If you have an example of an expert, you can use those types of techniques to try to back out what is the reward function that they're maximizing.
Very much, Greg. So you were so patient. You answered all the questions in the chat. So I think there is lots of things interesting that you guys are working, and I'm excited always to see that every time I see a presentation from you and your group, you always up your game and you have new interesting. So thank you very much for taking the time. I know you're busy, and taking the time to give this presentation to us was very helpful for our students. And thank you very much again. And again, if anybody has any questions, direct them to me, and I will ask Craig, and then we get it from there. So thank you very much, Greg. Thank you, everybody, for being here. And thank you very much, everybody.
Thank you for hosting us and all the great questions.